In this video, we're going to basically recap everything that we've done in rotational motion. And for each one of those things, I'm going to talk about how we can identify when to use each of those problem-solving techniques, from reading a problem and trying to learn when to apply certain things, and very importantly, when not to. So in green, I'm just going to put sort of the basic content that we've learned, and then in blue, and by the blue ones, I will put a little star. Those are going to be how you can recognize those problem-solving techniques. So the first thing that we did in rotation was rotational kinematics, right? So we did our standard rotational kinematics, and basically we did this for constant and non-constant alpha, right? So we learned how to apply our constant acceleration equations and how to apply integration and derivatives. So constant and non-constant acceleration, in this case angular acceleration. We learned the relation between alpha, your tangential quantities, and actually I'll just be more general than that because we also did it for velocity. We learned the relation between angular and linear quantities, right? We learned how to find the vector direction of angular quantities like omega or alpha using the right-hand rule. So I'll say here we learned to use the right-hand rule for omega to find the direction of omega and alpha. Now, in terms of problem-solving techniques, when do you know it's a kinematics problem? Really, very often it just reads like a kinematics problem in that you're given some initial information or you're given a function that involves time. So that's a key thing. If we think about the rest of rotation, it really doesn't involve time. So a thing that you're going to be on the lookout for is going to be that it involves time. Now, then you have to decide if it's constant or non-constant acceleration. But a main thing that I'm going to say here is don't go looking for kinematics if it's not obvious. So a lot of times people apply kinematics where it just doesn't belong. So for example, if this rod is horizontal and it swings down to the vertical here, a lot of people think, oh, well, I could find the torque. And if I find the torque, I get the acceleration. And then I can just integrate that, or not even integrate that. Then they say I have the acceleration, and I just have the acceleration. I can use my constant acceleration motion for this swinging downwards. And you can't, because this does not have constant acceleration as it swings downwards. And time's not involved in the problem. So if time's not involved, you really probably don't need kinematics. So that's going to be a big way to recognize whether or not you're going to want to use kinematics. All right, then we moved on, in this case, to Newton's second law, except for along the way to understanding Newton's second law, we had to learn about moment of inertia and finding torque, right? So we basically here, I'm going to put in that we learned about moment of inertia, which again is the rotational inertia of a system, so the rotational equivalent of mass. And we learned to calculate it with the parallel axis theorem, and we learned to calculate it by integration. And when we learned integration to get the total mass and the moment of inertia of a system. So really, in terms of problem recognition, there isn't one here because either you need the moment of inertia or you don't. But it is an important thing that we have learned. So the other thing then that we have covered in this class is going to be, like I said, Newton's second law. And that's why we really had put the mass there, just like we learned about linear inertia right before we talked about Newton's laws. So we did Newton's laws for rotation. And very specifically, we have the idea that the sum of torques is equal to the moment of inertia times the angular acceleration. And we learned that we have to use torque is equal to R cross F to get your individual torques. And so then that gives us the right-hand rule for the cross product that we also learned along the way. And so the idea here, right, that you add up all your individual torques, and then you set it equal to the moment of inertia times the angular acceleration. Now, in terms of problem recognition, I just said the key word, acceleration, right? So anytime that there's information about forces and you need acceleration, then this is the thing for you to use. So you're going to want to use Newton's second law for acceleration, and in this case, angular acceleration, right? And we can relate them. So remember that we have our relationship between our tangential and our angular quantities. Especially so acceleration when there's information about forces. Even something hanging in a gravitational field, that's information about forces, right? Because you know that the force is going to act at the center of mass, you know where it applies. So you have information about forces, therefore you can get the torque, and then you can set it equal to I alpha. So that's going to be a key thing to be on the lookout for in terms of problem recognition. All right, so after Newton's laws for rotation, that was modules 12A and 12B, we went on to discuss conservation of energy, with rotation, right? And so what we did here was we found basically that if we have a system that's pivoted, then we have K total is just 1/2 I omega squared. And if it's not pivoted, then K total will be that rotational kinetic energy plus 1/2 times, 1/2 times the mass times the speed of the center of mass squared, where the speed of the center of mass was equal to omega times r. As part of this discussion and deriving that V equals omega r, we also looked at rolling motion in general and looking at the total velocity, the velocity of the center of mass plus the tangential velocity at a point on a rotating wheel. So in terms of problem recognition for conservation of energy, well, it depends, and it's going to help you find speed. Now, the problem with this is so does conservation of angular momentum. So let's try to figure out when you can use each one. So in this case, it's going to involve speed, angular speed often. So that's going to be a key thing to look out for to separate it from Newton's second law. But it'll involve speed without a change in moment of inertia or a collision. But without a change in moment of inertia or a collision. And the reason is that energy, mechanical energy, is not conserved in those. When you change your moment of inertia and you bring your arms in, what we found is that you're actually doing work. So your mechanical energy is not the same before and after that event. When there's a collision, there's some delta U internal. Their mechanical energy is not the same before and after that event. So do not use conservation of energy if there's a change in moment of inertia or a collision. That's going to be the easiest way. Often, if you can rule out those things and it involves speed, you can give energy a try. But very often in terms of problem recognition, if there is a change in height of the center of mass, this bar swinging downward, and you want to find its speed at the bottom, then you're going to want to say, oh, look, there's a change in height of that object. So often it involves a change in height of the center of mass of an object. Okay. That brings us to our last one, which is going to be conservation of angular momentum. And conservation of angular momentum, like we saw, that can be calculated from R cross P or I omega. And then we saw that we can have the sum of all the initial angular momentums equal to the sum of all final angular momentums. So the sum of all initial angular momentums equals the sum of all final angular momentum. So our fundamental conservation of angular momentum. In terms of problem recognition, this involves speed as well, but it involves speed with either, and I'll put here, with either a change in the moment of inertia or a collision. Those are going to be the two things that you're kind of on the lookout for. It will not have a change in height. The main thing is that it applies immediately before and after the event. So after, say, the collision happens and the bar starts to swing, it's immediately after the bar starts to swing, so that the change in height of the center of mass is negligible. If there's a change in height of the center of mass as this starts to swing, the torque from gravity is not negligible anymore, and we have an external torque. So it applies immediately before or after a collision, or event. So we want to have no significant external torques for a significant time. So we apply this over a shorter time scale. Now, if somebody slowly brings their arms in on the ice, fine. It's still right before they start to bring their arms in till right after they're done bringing their arms in. So it's over the course of that event, assuming that there's no external torques acting during that event. So it's not for any part of a problem that involves a change in height. All right, so now what you can do is work through different problems, try to recognize when you're using each one, naming the problem-solving constant you're using, and even recognizing why you're using it. All right, as always, let me know if you have any questions.